Before starting talking about electronic configuration for ions, let's review what are ions. Ions are atoms of the same element with different number of electrons. When you have your elements as they are in the periodic table, they are neutral. Neutral elements have the same number of protons and the same number of electrons. Your protons are positive charges. The electrons are negative charges. So if you have the same amount of positive and negative charges, they will cancel out. What happens when you have ions is that the number of protons is not changing, but the number of electrons will be different. You will have more or less electrons. So let's look at sodium here. I have sodium, my element 11, electron configuration for the neutral atom of sodium, right? With 11 protons and 11 electrons. You have 1s2, 2s2, 2p6, 3s1. So you have 11 electrons in total, and that's what you have in the electron configuration, 11 electrons. The total number of electrons for any element is divided into two. We have core electrons, which are the inner electrons, and we have valence electrons. So everything that we're going to be doing from now on, it's based on the valence electrons. The valence electrons are the electrons that we have in the highest energy level. Remember, we have different energy levels where the orbitals are located, and we place the electrons in those different energy levels, specifically in the orbitals. So the highest energy level is the one that contains the valence electrons. Now, valence electrons are very important, and we focus on them instead of core electrons because valence electrons are responsible for the reactivity of the atom. The valence electrons can be transferred or they can be shared. When we say transfer, what that means is that electrons can be given up or an element can gain electrons. If an element is given up electrons or gains electrons, what you're getting is an ion. So an element losing electrons will have more protons than electrons, and it will have an overall charge that is a positive number. An element that is gaining electrons will form negative ions. So you will have more electrons. If it's gaining, it will have more electrons than protons, and you will have an overall charge that is a negative number. Now, looking again at the electron configuration for sodium, I have underlined the electron configuration using two different colors. In yellow, I have the 3s. And then everything else, it's underlined in that pink color. So you have the electrons in the first energy level and second energy level with a color, and then we have the electron in the third energy level in yellow. If you look at the different energy levels for that electron configuration for sodium, we have electrons in the first energy level, the 1s2, electrons in the second energy level, those two electrons in that s orbital in the second energy level, 2s2, and we have also p electrons in the second energy level, 2p6. Now, on the third energy level, we have the s orbital with one electron. Out of the three energy levels, 1, 2, and 3, first, second, and the third energy level. The third is the highest energy level. So that energy level, it's underlined in yellow because it's the highest energy level. And you have just one electron, this one right here. That electron, it's a valence electron for sodium. Valence electrons, electrons located in the highest energy level. For sodium, the highest energy level is the third one, and you have one electron. So that's one valence electron for sodium. We can actually assign the number of valence electrons using the periodic table. Sodium is in group 1 and it's going to have one valence electron. Looking at group number 2, electron configuration for sodium ends in 3s1. For magnesium in group 2, we are going to have 3s2. So for magnesium, we're going to have two valence electrons, but not just for magnesium. Everything in group 2 will have an electron configuration that ends in S2, okay? Depending on the period. For beryllium, you have 2s2. For calcium under magnesium, you will have 4s2. Okay? But everything is s2. So group 2 will have two valence electrons. When we move to the right side of the periodic table, we start with group 3 all the way to 8. And the group number, it's actually telling you how many valence electrons you have for each group. So you can predict the valence electrons for gallium. Gallium, it's in group 3 in the periodic table. It will have 3 valence electrons. Let's look at selenium. Group 6 in the periodic table, it will have 6 valence electrons. So you see how I wrote my group numbers here in yellow, because yellow represents the valence electrons, but it also represents the group number. So to determine how many valence electrons you have for an element using the periodic table, you don't have to write down the electron configuration. You can compare the electron configuration. You can look at the valence electrons from the electron configuration, but you can actually determine that number just by looking at the periodic table. Valence electrons, it's equal to the group number. Now, valence electrons for ions. Okay? Positive ions losing electrons, negative ions gaining electrons. So for sodium, we have the electron configuration 1s2, 2s2, 2p6, 3s1. Now, the ion of sodium is Na plus 1. The sign is telling you that it's losing. The number is telling you how many electrons it's losing. So the atom of sodium, neutral atom, with the same number of protons and electrons will have 11 protons, 11 electrons. Sodium plus 1, losing 1 electron, will have 11 protons. That number is not changing because that's your atomic number for sodium. But now, instead of having 11 electrons, if you have a charge of plus 1, losing 1 electron, the ion of sodium has 10 electrons. So we can write down now the electron configuration for Na plus 1. Na plus 1, 10 electrons. So we're writing an electron configuration for 10 electrons, not 11, because we have the ion with a charge of plus 1. One is 2, 2 is 2, 2p6, and we have 2 electrons, 4 electrons, plus 6, that's a total of 10 electrons. So let's write down the electron configuration for some ions. Starting with potassium. Potassium in the periodic table, it's element number 19. So if you have a neutral atom of potassium, you will have 19 protons, 19 electrons, right? The same number of protons and electrons, and it's given by your atomic number. When you have the ion of potassium with a charge of +1, a charge of +1 is telling you the positive that it's losing the number how many electrons. So potassium +1, it's the ion of potassium when your element, the neutral element, loses 1 electron. So your neutral atom of potassium losing 1 electron, instead of having 19, it will have 18 electrons. So what you're writing down is the electron configuration for 18 electrons instead of the electron configuration for 19. Whenever you're writing the electron configuration, you should make sure that the number that you're writing down for electrons matches the total number of electrons that you have. So I have 2 electrons here plus 2 here, that's 4, 10, 12 plus 6, 18 electrons. So the second one is calcium. Again, calcium, the neutral element calcium, has 20 electrons. Your atomic number is 20. You have 20 protons, 20 electrons. The charge of +2 is telling you that it's losing 2 electrons. So now you don't have 20 electrons. You will have a total of 18 electrons again. So you can write down the electron configuration for calcium +2 or the ion of calcium, and it will be exactly the same one that I have for the ion of potassium with a charge of +1. The third one will be aluminum +3. Aluminum +3, aluminum you have a atomic number equal to 13. If it's +3, it's losing 3 electrons, so you have now 10 electrons. At 10 electrons, you have to write down the electron configuration corresponding to 10 electrons instead of 13 because you have the ion of aluminum. So 1 is 2, 2 is 2, 2p6. We have to stop right there. That's 2, 4, and 6. That's 10 electrons. The next one I have P minus 3. So phosphorus with a charge of -3 or the ion of phosphorus. So we check in the periodic table P, it's element number 15. When you have the ion of P with the charge of -3, minus the negative sign indicates that that element is gaining electrons, the number how many. So you go from 15 gaining 3, that will give you a total of 18 electrons again, which is the same electron configuration that I wrote for potassium +1, which is the same that you will have for calcium +2. And now we move to S minus 2. So S is element number 16. 16, when it's neutral, when you have the charge of -2, that one is gaining 2 electrons. So instead of 16, when you have the neutral atom as it is in the periodic table, 16 protons, 16 electrons, when you have the charge of -2, it will go from 16 to 18 electrons again, which is the same electron configuration that you have for potassium +1, calcium +2, phosphorus -3, 18 electrons. Cl -1. So checking Cl in the periodic table, it's element number 17. Neutral atom will have 17 protons, 17 electrons. This is the ion with a charge of -1, which means that your element is gaining, the atom for that element is gaining 1 electron. If it's gaining 1 electron, it's going from 17 to 18. One more, so I can explain new things in here. So nitrogen, the element nitrogen, it's element number 7 in the periodic table. Atomic number 7, neutral atom for nitrogen, has 7 protons, 7 electrons. When you have the ion of nitrogen with a charge of -3, it means that that atom of nitrogen gained 3 electrons. So it's going from 7 gaining 3 up to 10 electrons, which is the same electron configuration that I wrote for aluminum +3. 1s2, 2s2, 2p6. Now, if we check the periodic table with all of these ions that we have, we can actually see a pattern, and we can actually kind of predict the charges for different ions looking at the periodic table. You see, for all of them, we have 18 or 10 electrons, including sodium in the previous examples. And so for sodium, we have a charge of +1. It goes from 11 to 10 electrons. So we have 18 or 10 electrons. If we check the periodic table, element with 10 electrons or an electron configuration with 10 electrons is neon. An element with an electron configuration containing 18 electrons is argon. Both of them are in the group 8, your noble gases. Your noble gases, they have 8 valence electrons. They are in group 8, so they have 8 valence electrons. That's the maximum number of valence electrons that an element can have. All of them, not just neon and argon, everything below helium, not helium, neon, argon, krypton, will have an electron configuration that is s2p6. Neon, it's in period 2, so that will be 2s2, 2p6. Argon, it's in period 3, so that will be 3s2, 3p6. Krypton, it's in period 4, so that will be 4s2, 4p6. S2p6, they have 8 valence electrons. That's the last thing that you will have in your electron configuration for your noble gases. Every element in the periodic table wants to have 8 valence electrons. So your ions, the elements, are giving away electrons, gaining electrons, or what we're going to be learning in the future, sharing electrons. But regardless of what they're doing, gaining, losing, or sharing, it's always to have the same electron configuration as a noble gas. Noble gases, they have 8 valence electrons, which means that they are very stable. They have the maximum number. They don't want to give any of those electrons away. They don't want to get any electrons, additional electrons. So you see how potassium is going from 19 electrons with a charge of +1 to 18 to have the same electron configuration as argon. So the metals in the periodic table, they will lose electrons to have the same electron configuration as a noble gas. The non-metals in the periodic table, they will be gaining electrons to have the same electron configuration as a noble gas. Let's look at potassium. Noble gas, potassium is 19, so we have noble gas with 18 electrons. That's 1 electron less than what you have for potassium. And if you move further to the front, like to the back, you have argon. Moving forward, you will have krypton with 36. If potassium wants to have the same electron configuration as a noble gas, right? The closest ones to potassium are argon, krypton. You can have also neon close to potassium with 10. For potassium to have the same electron configuration as neon, it will have to lose 9 electrons to go from 19 down to 10. For potassium to have the same electron configuration as krypton, it will have to go from 19 all the way to 36. So it will have to gain 17 electrons. You see where I'm going? To go to neon, same electron configuration as neon, it will have to lose 9 electrons, 19 down to 10. To have the same electron configuration as krypton, it will have to gain 17 electrons to go from 19 to 36. The easiest one is for potassium to lose just 1 electron to go from 19 down to 18 and have the same electron configuration as argon. Now I'm going to look at other elements in the periodic table. Let's check the ones that we have here. Let's check P. (15). We have 10 right here. We have 18 right here. For phosphorus to have the same electron configuration as neon, it will have to go down from 15 to 10. It will have to give away 5 electrons. For phosphorus to have the same electron configuration as argon, it will have to gain just 3 electrons. So phosphorus is a non-metal. Since they're close to the noble gases, close to group A, because your non-metals are on the right side of the periodic table, it will be easier for the non-metals to gain electrons than to give electrons away. It's easier for phosphorus to gain 3 electrons and get all the way to 18 than to lose 5 electrons to go all the way to 10. So that's why the non-metals are forming negative ions. You see, I have phosphorus with a -3, I have sulfur with a -2, nitrogen -3, Cl -1. So nitrogen, it's element number 7. For nitrogen to have the same electron configuration as helium, it will have to lose 5 electrons. So it will be easier for nitrogen just to gain 3 to go from 7 to 10. Now, the charges that I'm giving you here for the ions, we can actually predict them using the periodic table. The number of valence electrons for group 1, it's 1 valence electron. So elements in group 1, remember, the valence electrons are the ones that are being transferred. So giving away electrons, gaining electrons. If you have 1 valence electron in group 1, elements in group 1 can give away 1 valence electron. Something that is given away 1 electron will have a charge equal to +1, plus giving, and the 1, how many? Group 2, it's 2 valence electrons, right? So those elements in group 2 can give away 2 electrons. They are metals, and the metals will always be forming positive ions. So for group 2, we have charges equal to +2. Magnesium, the ion of magnesium has a charge equal to +2. The ion of calcium, right there in the list of ions that you have, a charge of +2. The ion of strontium right under calcium will form ions with a charge of +2. So ionic charges using the periodic table we have for group 1 +1, for group 2 +2. Now we move to the right side of the periodic table. You have aluminum right there, which is in group 3, and the ion of aluminum will have a charge of plus 3. Plus 3 because group 3 you have 3 valence electrons. When aluminum gives away those 3 electrons, will go down to 10, which is the same electron configuration as neon. So in group 3, I'm going to put in general a charge of plus 3. That applies for aluminum and gallium. And then we're going to move to the negative part. I'm going to skip group 4 and I will tell you why in a little bit. So you have nitrogen right there, phosphorus right there, and I gave you a charge for those ions, right? I'm giving you the charges here. Then we write down the electron configuration, and now we're relating that information with your periodic table. For nitrogen and phosphorus, we have a charge of -3, but not just for those two. That applies to everything in that group or family. So group 5 in the periodic table, they have 5 valence electrons. Okay? To go to a valence electrons, they need to gain 3. That's why they're forming ions with a charge of -3. Now we move to group 6. And group 6, you have 6 valence electrons. To go to 8 valence electrons, the same that you have for your noble gases, they will have to gain 2 electrons. So they will form ions with a charge of -2. In group 7, you have 7 valence electrons for those elements. For those electrons to have 8 valence electrons, they need to gain 1 electron. So they will form ions with a charge equal to -1. Now, group 4, we're not going to assign a charge using the periodic table for group 4. I'm going to give you just one example. If you check carbon, atomic number for carbon is 6. So for carbon to have the same electron configuration as, let's say, helium, noble gas, atomic number 2. Right? So for carbon to have the same electron configuration as helium, it will have to go from 6 to 2 electrons, which means that it will have to lose 4 electrons. 6 losing 4, that will give you 2, which is the same number of electrons that you have for helium. But carbon with 6 electrons, right? If you look at neon, 10 electrons. For carbon to have the same electron configuration as neon, it will have to gain 4 electrons. So it's the same number of electrons to go to the same electron configuration as helium or neon. So in this case, since it can be one or the other because it's the same, you can think about this as the same amount of energy. Same amount of energy, it's related to losing 4 or gaining 4. Since it's the same, we cannot predict a specific charge using the periodic table. For the other main groups, 1, 2, 3, 5, 6, and 7, in general, the ions will have the charges that I'm writing here, but not for group 4. We can determine the actual charge for an element in group 4 when it's in a compound, and that's something that we do in the future.